Thank you. Well, first of all, thank you very much to ICMS and especially Dawn for everything you've done to make this happen. Thank you, Martin, for that introduction. And thank you, everyone, for coming along to listen to me talk about inclusion-exclusion in mathematics. I am going to talk about some things I've learned in the process of my slightly curious career direction. And I am also going to introduce category theory. Now, this is probably the oddest audience that I've ever spoken to, seeing as there's over 100 actual category theorists and some people who are not category theorists. And I would like to assure the non-category theorists that I'm not going to make the category theory harder just because there's a bunch of category theorists in the room. And so the category theorists are not going to learn any category theory, but the category theorists might see some surprising applications of categorical thinking and some surprising ways of using the categorical way of thinking to investigate issues in the broader areas of inclusion in mathematics and in the world beyond. And so these two themes will go parallel to each other. So as you may or may not know, I used to be more of a sort of normal maths lecturer in a normal university, although some of you may say there was nothing ever particularly normal about me. However, I changed career, sort of, and now I teach art students. The School of the Art Institute is a university that is a kind of, as they call it, elite art school. And so it's a university, the students are very serious, but they're very serious about art, and they are not very serious about mathematics. And I think this is my dream job, because I am teaching mathematics to people who are very serious thinkers, but who have different ways of thinking and who really care about the world and society. And I've learned so much from teaching them, because I'm sure you all agree that teaching at its best is a two-way process. It's not just that we stand at the front and impart knowledge, but hopefully we also learn things from our students, and then the knowledge goes around and in a virtuous circle and grows. And I've learned so much from my art students that I would like to share as widely as possible, because the art students are very, very self-aware, and they're very keen to talk about their experiences of mathematics. And most of their experience of mathematics is negative. And so there's a lot to learn from them about why they were put off mathematics and how they can be, as it were, put back on mathematics, which is what I've been doing for the last few years. So what I'm going to do in this talk, it's got two parts. The first part is general, where I'm going to start by talking about my background in teaching math students and then art students. And then I'm going to talk about my theory of how we could talk about character types rather than always focusing on gender. So sometimes gender really is an issue when it's about bias, prejudice, exclusion, harassment, things like that. And sometimes it really isn't the actual point, I think. So I'm going to talk about how we can focus on character instead. And I'm going to talk about how this can guide us to a way of more inclusive mathematics. Because diversity is only about the numbers of different kinds of people involved. Inclusivity is about how much they feel part of the subject and how much they are included in it. And I'm going to argue that category theory is a very good place to do inclusive mathematics. And in fact, I've been teaching category theory to art students as a way of bringing them back into mathematics where they have previously felt kicked out. And this is not an obvious thing to do. Usually, and most of the category theorists in this room probably only started learning category theory either when they were actually PhD students in pure mathematics or computer science, or possibly even later, or perhaps when they were very advanced undergraduates. And usually the accepted wisdom is that you can't teach category theory to people until they have all this other knowledge in mathematics already. And yet I've decided to bypass all of that and teach it to art students, some of whom can't do their times tables. So I'm going to talk about ways in which category theory is inclusive, then talk about how it focuses on relationships, that it gives us different ways of thinking about how things can be the same, and how it puts things in context. And I'm going to link this with the ideas of social questions about inclusivity and some of the political questions that tax many of us in the current era. So first of all, my background, I used to teach in kind of normal maths universities. And all the students had done very well in school maths. They thought they were great at maths. They all arrived at university thinking they were going to be the best person at maths, because they always had been the best person at maths. They were going to go into careers in maths and science and maths-related things, and it was very male-dominated. The last calculus class I taught at the University of Chicago had less than 30% of the class being women. And there was something sort of difficult about teaching that audience, because they would all arrive thinking they were going to be the best person in the class at maths, but you can't all, you get there and they couldn't all be the best. And so a lot of them were very sad at the beginning. Whereas in art school, most of them did not do well in school maths, and they all arrive thinking they're going to be the worst at maths, and they can't all be the worst. So it's actually very happy in the first few weeks, where they discover that for the first time they're not the worst person in a maths class. They're all going to go into careers in art, design, technology, teaching, photography, and possibly teaching. And also, it happens to be very female dominated. So my classes have been typically more than 90% female. And actually, I usually have more trans students than white male students. And I've been wondering about, so questions start arising, right? I'm often asked about the issue of being a woman in a male-dominated field, because I am, and I used to be very reluctant to address these questions. In the early part of my career, I never wanted to talk about it, ever, because I didn't want to draw attention to the fact that I might be different and that there was a chance to stereotype me. But now, I realize that it's important for people to speak out about it, especially on behalf of those who, like I previously was, feel like they can't speak out because they're earlier in their career or they don't feel secure in their positions. And I've been thinking about how this relates to the fact that my art students are much more female dominated and were mostly put off maths in the previous part of their lives. So what I've done is that I spend a lot of time talking to them about their previous experience of maths. And the first exercise I give them is to write their mathematical autobiography and tell me about what put them off maths before. And now, this is not a random peer-reviewed large sample experiment. However, I've now been teaching there for about 4 years, and I've had about 80 students each year. Our classes are capped at 20. And so, well, maybe some of us can multiply 80 by 4, but that's a number of students. And there are clear themes that arise in what they say, and they are that they hated memorization, that they hated, in particular, memorizing their times tables, that they can't stand formulae, that they don't like getting things wrong, that they have a false dichotomy idea. I mean, we know it's a false dichotomy between art and maths, and that they perceive that there is a lack of creativity in mathematics. Now, these reasons make me very sad, because they're basically the exact same reasons that I love maths, except the other way round. So the reason I loved it was that I felt I never had to memorize anything, because as long as I understood it, right, there's lots of nodding going on from people with green bands around their necks. But as long as you understand it, you don't have to memorize anything. And at risk of making a few people get cross, I'll say that was why I didn't like physics, because I always felt like in physics I had to memorize things. So I definitely never memorized my times tables. Now, this provokes horror, especially in parents of children of a certain age. But it doesn't mean I can't do my times tables. I can do them. It's just I didn't exactly memorize them. I understood the relationships between numbers. And I very quickly use things like I picture grids, or I use rules of relationships in order to do them very quickly without tiring myself out. Formulae, to me, are like explanations of things and magic machines that save you effort of doing things over and over again. And it's true that in the early part of my life, I didn't get things wrong maybe as much as some other people did. But in the end, I think that maths isn't so much about right and wrong as about uncovering and illuminating things. And I know that art and maths aren't a clean dichotomy. And as for the lack of creativity, this is a really important one, especially because I keep reading articles in the media by journalists, and most journalists do not have mathematical backgrounds because they've gone into journalism for other reasons. And so many of them say the following argument. They say, in the coming future, robots and AI are going to take over much of our lives, and so it's going to be much more important for humans to do things that are, to have creativity, because that's the thing that humans will be able to contribute while robots are doing all the other stuff. And they say, therefore, we should not be focusing on teaching STEM subjects, because we need to focus on the arts, because that's where you learn creativity. Now, I support this argument up to that last point. Because we know, I hope, that maths and science do involve creativity. It's just that sometimes maths and science classes don't involve creativity. And I'll tell you an example. When I was at school, I hated all sport, and one of our PE lessons was called dance. And what it consisted of was a dance teacher who picked some dreadful electronic music, made up a choreography, and forced the whole class to learn the exact same choreography and do it in unison to this dreadful music. Now, that involved no creativity at all, but I managed still to believe that dancing involves creativity in general, but just that that class didn't. And I think the trouble is that many of my art students have come through school and developed the idea that there is no creativity in mathematics. And when I show them that actually mathematics is not the thing that they thought it was before, they become interested in it again. And here's some electronic music, and we could all do a synchronized dance to it, or we could switch it off. So the story that I used to tell about my interesting career diversion is that in the early part of my career, I felt that I should hide all signs of femininity so that I wouldn't give people a chance to stereotype myself. And when I first was an undergraduate, it was about 10% of the undergraduates who were women, and it sort of got worse as I went through my PhD. And the first conference I went to, and some of you were there, and I met you, and you're lovely, and it was a great conference, but I think that there were about 100 people, and there were 3 women. And there were 4 women's toilets. And so the advantage was we never had to queue for the loo. But apart from that, that did stick in my mind. So I was always trying not to stand out in that way. And then when I became more secure and I had a permanent job at the University of Sheffield, I started feeling like it might be all right to demonstrate some signs of femininity. So I started doing that, but only outside work. And so I had this odd split life where I was somehow kind of feminine outside work and not inside work. And then I felt odd having this split life. So I tried to blend them. And then I realized I hated my job. So then I left. And it was slightly less dramatic than that. It took a bit longer. And then after I had left for a while, I realized that that narrative doesn't make any sense. Because everything I do is feminine, because I'm a female person. And the fact that we associate characters to genders is an outdated and it's a prescriptive way of talking about things, which I think is unhelpful to men, women, and also non-binary people. And there is no reason to carry on doing it, that we should have stopped doing it ages ago. And it does things like it means that men are under pressure to be a certain way to emulate traditional masculinity, and that women are simultaneously told that they need to be more like that in order to be successful. But then at the same time, if we are more like that, then we're told that we're aggressive or loud or too ambitious or something. And so nobody can really win under those circumstances. And it's not really about men and women, it's about certain characters. And I know plenty of men who have felt oppressed by the classic pressures of old-fashioned masculinity, as well as women who haven't fitted into the traditional forms of classic femininity. And I think that we need new terminology in order to get away from thinking about characters as related to genders. And then we can think in a much less divisive way about what character types we want to value in society and which ones are good for mathematics, in fact, and which ones are also good for science, for research in general, for, dare I say it, politics. I promise I won't say that word too many times. So I decided that we need new words. And so I brainstormed for a few years to come up with some words. And the words I've come up with are ingressive and congressive. And etymologically, ingressive is to indicate going into things, and congressive is to indicate bringing things together. And the first thing I want to stress is that this is not supposed to be a clean dichotomy. And no matter how many times I stress this, somebody objects afterwards and says, but it's not a dichotomy. But I say it's not a dichotomy. So it's not a dichotomy. I think it's more of a two-dimensional, 2 axes. And you can be more of one and more of the other. You can be some of both. You can be different things at different times, right? It's not fixed. I'm definitely not claiming that this is some kind of biological thing. In fact, what I think is that society has been rewarding ingressive behavior for so long that everybody has veered to be more and more ingressive as much as they can in order to be successful. And that's what I realized I did. I tried to be as ingressive as I could to be successful, or what I perceived was necessary to be successful in an academic career. And then I realized I didn't like being that, and I wanted to do something where I could be as congressive as I wanted to, and that's what I feel I've been doing in the 6 years since I changed the direction of my career. So I actually think it's kind of like this. So it's not even, sometimes when one is trying to be very nuanced, you sort of say it's a whole spectrum, it's a grey area, but it's more than a grey area, because if the top left is very red, right, and the bottom right is very blue, and then they combine towards the middle, but there's also intensity. So as you go towards the top right, there's how intense it is, and then it's more white towards here. So it's some kind of two-dimensional version of a spectrum. We have many higher dimensional mathematicians in the room, and I like thinking in higher dimensions, which gives us more nuance. Anyway, I think that my path through life consisted of starting down here somewhere and then veering up in towards the red area, if we think of that as ingressive, realizing I didn't like it there, and then moving myself back down again. So here are some characterizations of how I think of ingressive and congressive behavior. I think that ingressive is often about being competitive as opposed to collaborative. And it's often about focusing first on the self and the individual rather than the community around us. So of course, again, these are not dichotomies, right? You can do some of both, and often individuals are part of the community and the community is made up of individuals. But for example, I've realized in thinking through many of the extremely terribly divisive political debates of the last few years, that the fundamental difference between the political views I have and the people I disagree with, the fundamental difference often boils down to how much we believe in a community as opposed to individuals looking out for themselves. So ingressive people like winning, and you might think that everyone likes winning, but actually some people hate anyone losing at all. And so I don't like the idea of beating other people. I don't like being beaten. So if somebody has to win, then I'd rather win. But I'd really rather there were no winners and no losers, and that everybody could make something together. And this may sound extremely utopian, but I think education is like that, right? In an education situation, hopefully we're all learning together. We don't have to beat someone out in order to learn something. You don't have to actually take away knowledge from somebody else, right? It's not a zero-sum game. We make more knowledge together. I also play music, and when you're playing chamber music, you're not trying to beat the other people out, or at least if you are, then you're not really doing it very well, I think. So ingressive people like showing that they're clever, but congressive, it's more the worry about being thought stupid. And so as a result, ingressive people, whether it's students or indeed people at conferences, are more likely to call out answers or ask questions, and congressive people are reluctant to speak up. And I don't think it's quite the same at our conference for various reasons, but I have been keeping a tally of who's been asking questions. And at the talks I've been to so far, there have been 85 questions from male people and 3 from female people. And 1 was from me because I was so determined to change that statistic a bit. Ingressive people like solving problems, I think. And congressive people, it's more about making connections. And this is often thought of as a stereotypically male and female thing, because men like solving problems and women like, sharing problems and empathizing with each other. And whenever you say those things, you have to say, but not all men and not all women. And then you get into these situations where you keep having to add these caveats on. But if you just never associate it with gender in the first place, then you don't have to have those caveats. And then you can just look at who likes solving problems and who prefers making connections between people. Ingressive people, I think, like right and wrong, sort of black and white situations. And it's funny because often maths undergraduates I taught before, I would ask them why they were doing maths. I always ask my students at the beginning of the class, what are you doing in this class? What are you doing in a maths degree? And why are you even in university in the first place? And it's sort of shocking that they haven't thought about it. But often they say, I really like maths because it's easy and there's clear right answers. And I think, oh dear, that's not a very good reason to like maths, because it's not going to stay like that for very long. And congressive people sort of prefer creating and building things. And when my art students are not interested in questions that have right and wrong answers, because they're really interested in nuances and ambiguities. And when I show them that maths can be about creating and building and exploring, they become much more interested in it. So this is an interesting one from my experience of teaching, which is again not a large random peer-reviewed thing. But ingressive people, I think, overestimate their own abilities. And in my experience, it has most often been male students in the first year who think they're great and think they're doing fantastically when actually they're doing awfully. But then they don't ever come and get help because they think they're doing well. And then there'll be female students who'll come and cry in my office because they think that they think they don't deserve to be there, they're doing terribly, that everyone else seems to know more than them, and actually they're doing fine. And they'll come and get help all the time, and then they're the ones who do fine, but they don't realize they're doing fine. And I think maybe school maths is presented so ingressively that that encourages ingressive people to like school maths, and that congressive people are put off school maths. Perhaps. I was very put off by school maths. I was just lucky that my mother showed me interesting things about maths that were less ingressive, although I didn't have the language to say it at the time, that made me hold out hope that if I could just make it to a PhD, then I could do congressive mathematics again. And it now seems ridiculous to me that I had to do so many years of ingressive mathematics in order to qualify to do congressive mathematics. So what do I think congressive mathematics is? I think that ingressive mathematics is more about outcomes and answers, and that congressive mathematics is more about the processes. That ingressive mathematics is about facts, and that congressive is about discovery and investigation rather than the facts themselves. That ingressive is more about speed, and that congressive is more about depth. And perhaps those of us who are familiar with what research maths is like will know that the kind of speed that you have to do well in exams is not the same as the kind of thinking that you do for research, where you might think about something slowly for 5 or 10 years or more. So ingressive might be about formulae as opposed to congressive about reasons and explanation. And ingressive may be more about strings of symbols, and congressive maths is about visual and physical aids that you can interact with and manipulate. And that ingressive maths is about rules, and many people who've been put off maths perceive it to be just a set of rules that somebody imposes on you, whereas congressive often involves choices and opinions, and that's what research maths is about. And that ingressive maths seems to be about solving problems, and that many people think the whole point about maths is solving problems, whereas, especially the kind of research I do, and many of us in the room do, it's about building structures more than about solving problems. So as opposed to calculating answers, it can be about uncovering relationships. And this is one of my favorite relationships to uncover, where you can insert a bagel into a slinky. And that demonstrates that the surface of a bagel is the same as what happens in the field of topology, which is about spaces. If you take a circle and you kind of wave it around in a circle, that's what the slinky is. And everyone says to me, how do you do that? And how you do it is you cut the bagel and then you put it in. So I also teach maths much more congressively now, and this involves, instead of traditional lecturing where someone stands at a board, and I'm sure many of us have experienced this, that you stand at a board and you write as fast as you can, and then the students write it all down as fast as they can, and it's what we used to say, it's a method for transferring knowledge from the board to the paper, bypassing the brain. And whereas what I do now is I just engage the students in projects where they can discover things. Instead of it being about right and wrong answers, the projects have a low floor and a high ceiling, which means that there's a low point of entry so everyone can get in, but there's really no limit to what you can learn from it. And it is slower than simply throwing information at people that you have to swallow at high speed, but it's more interesting and more deep, and it engages people more. So one of the projects I do with my art students is we build the Platonic solids. The Platonic solids are the three-dimensional shapes that are very highly symmetrical. I don't tell them what the Platonic solids are. We cut out shapes, and then we just sit there and stick them together to see what we can make that's symmetrical. And some of them will build the Platonic solids. And some of them will build things that are very symmetrical but aren't quite the Platonic solids. And some of them will build a dinosaur. And that's fine, because what you discover if you build a dinosaur out of shapes is that pentagons are a terrible shape to try and build a dinosaur with. Whereas triangles are a really good shape to build a dinosaur with. You can build practically anything with triangles. And this is a profound mathematical fact. The fact that you can build things from triangles gets used at all levels of research. And one of my students, who's a fashion design student, went away and made a whole dress out of triangles after this experience. I thought that was great. Maths competitions are extremely ingressive, and as a way of doing outreach, I think it's problematic because it will put off people who don't like competitions. I don't like competitions. If anyone had put me in for a maths competition when I was a teenager, I would have hated it, and I would have said, oh dear, I probably shouldn't be a mathematician because of this. Whereas, in fact, I'm all right as a mathematician. I've done all right. I've had a career as a mathematician. I've done some research. I just prefer situations that don't involve competing with each other. So maths festivals and fairs where there's loads of activities and there's no particular aim, you can just explore. I like those kinds of things as outreach. And often there are questions about how we can get more girls into competitions. And I think that's not quite the right question. I think the right question is how we can value congressive mathematics more and do more congressive maths outreach. And with these words, we can say that. Without these words, we have to say really stupid sounding stuff like, we need to do more outreach that will be attractive to girls rather than boys. And that's really stupid, because then you get stuff like pink Lego that people think will attract girls. So sometimes people say, oh, the way to make maths fun is to turn it into a game. And that's all very well if you like games. I don't like games. I don't like any games. And so maths games are not fun to me. But I like making things. And so maths crafts are really fun to me. The kinds of things like magnetiles, where you just stick them together and you make something. So puzzle books are also very off-putting to me. I love this book, Which One Doesn't Belong, by Christopher Danielson. So each page has 4 shapes on it, and the question is, which one doesn't belong? And of course, the answer is any of them might be the one that doesn't belong. So every answer is correct. It's really about what explanation you are using to justify which one doesn't belong. And I particularly like the fact that the last page is a which one doesn't belong. It's a kind of meta which one doesn't belong. So that's what I think of congressive math. So how is category theory congressive? I'm going to argue that it's about understanding structure, not just problems with answers, that it focuses on relationships between things, which is what congressivity is about, and that it gives us different ways in which things can be the same or not. So that it's not just about right and wrong answers. And my wonderful PhD supervisor, who happens to be Martin Hyland, who just introduced me, taught us this he always said this phrase, there is a sense in which. And it helped us to focus on the fact that things just aren't right or wrong, but that there's always a sense in which this could be right and a sense in which something else could be right. And I think that category theory gives us a way of saying, well, in what sense is this the thing? And in what other sense is this other thing the thing? And then we can have more sensible conversations about many disagreements in life, I think. So it's about making connections between different ideas. And that's a very congressive thing, making connections between people, ideas, and situations. So I like to say that category theory is the mathematics of mathematics. I found a citation for this the other day on the internet, but it turned out to be me. So I'm not sure if someone else said this before. So I say that mathematics is the study of how things work. Right? It's not just about numbers and equations and about answers, even though that's what it can seem like. So it's not the study of how any old things work. It's the study of how logical things work. And it's not any old study of how logical things work. It's the logical study of how logical things work. And the trouble with that is that nothing behaves logically, really, in life. And that's why we have to forget some of the details about the things in life, so that they move into a place where they do behave logically. And that's the process of abstraction that takes us from the real world of things we can touch into the abstract world of ideas where things do behave logically. And it can be scary making that move, because you don't have your feet on the ground anymore and you can't touch things. And also you can't, in the abstract world, win arguments by yelling. And some people like winning arguments by yelling. I could, I'm quite loud, but I prefer not to do that. So if we unravel this definition now, I seem to be saying that category theory is the logical study of how logical things work, which sounds very looped up on itself, and sometimes category theory gets accused, even by other mathematicians, of being too abstract. Now I'm going to show, and this is what I talk to my students about, I'm going to show that abstraction has a purpose, and that the purpose is to be able to bring in more examples, actually. And so what you do is you sort of go higher in order to be able to pivot further and to include more things. And I'm going to include some examples that might be surprising, especially if you're a category theorist. So here's my favorite example of abstraction. It is the standard map of the London Underground, which is not geographically accurate. And it's an abstraction because it's forgotten many details about the situation, apart from which stations connect with other stations via which lines. And it's very practical for getting around London, because you can quickly see how you can connect. But it's not geographically accurate. So it results in sometimes hapless tourists trying to take the train from somewhere to somewhere else that's actually right next to each other, and you could walk there in 3 minutes. So here's the geographically accurate, more accurate picture of the London Underground. This one would be extremely difficult to use. But it's kind of interesting. I think it's interesting seeing how it actually connects together. It's not that one of them is right and one of them is wrong, right? Abstractions aren't right and wrong. Different abstractions focus on different aspects of the situation and allow us to focus on the thing that we feel is relevant at that moment. And the important thing is to remember that you're not claiming that's the whole situation. You're claiming that this is one aspect of the situation that you are illuminating right now. And the important thing is to be able to move and abstract in a different direction and focus on something else at a different time. And the key is not to pick the most abstract possible version. And again, this is something that I learned from Martin. The key is to pick a good level of abstraction for what you're trying to do. So when abstraction is done for no particular reason, then it does seem a bit contrived. So I'm going to talk about one version of abstract relationships, but we can start by talking about real relationships. And this is the kind of thing category theory starts with, looking at relationships between things. So for example, if A is the mother of B and B is the mother of C, then we can compose those things up and discover that A is the grandmother of C, right? This is something we do with relationships in life. And similarly, if A is the sister of B and B is the mother of C, then A is the aunt of C. And this is called composition in category theory. And what it means really is that we can omit arrows that we could have deduced from the situation already, which is these red ones. So if we know that somebody is the mother of someone, then we don't need to specify in extra that that's a grandmother. So a category consists of some objects, some things like that, relationships, and we call them morphisms because they might not actually be like relationships in the end. Composition, which is what that was, identity, saying everything is the same as itself, and then associativity and unit laws. So here's what associativity says. Associativity says is that A is the mother of B and B is the mother of C and C is the mother of D, then there are two ways we could think about this. We could go, oh, well, A is the grandmother of C. If A is the grandmother of C who's the mother of D, then that's her great-grandmother. And the other way around, we could say, oh, well, actually, B is the grandmother of D, but also A is the mother of the grandmother, and that means the great-grandmother. So what associativity is saying is that the grandmother of my mother is the mother of my grandmother. Commutative squares are things that crop up a lot in category theory. And the first commutative square I ever met, actually, it turns out it was when I was very little. I just didn't think of it as a commutative square at the time. And just like often, you may be doing maths even when you don't realize it. And I think we're often even doing category theory when we don't realize it. So when I was little, we had these curious family friends. There were these two brothers, I'll call them A and B, and there were these two sisters, C and D, and they married each other. And so the two brothers married the two sisters. So A was the husband of C and B was the husband of D, right? So now, going around the top right way, right, A is the brother of the husband of D, which means brother-in-law. And A is the husband of the sister of D, which is also your brother-in-law. But usually, the brother of your husband isn't necessarily the same as the husband of your sister. But this turned out to be the same, and this really intrigued me when I was little. And another one that I met more recently was to do with, I was at a party and some people were playing Super Smash Brothers, which I'd never seen before, and I'd also never met any of these people before. And they told me this story I couldn't in any way understand until I drew this diagram. So it was that there was someone called Alex who also turned out not to be called Alex, but I'll just call him Alex anyway. And he was really good at Super Smash Brothers. And he went to high school with someone called Spencer, and then he went to university with Nate. And then Spencer went back home and said to he went to university with Greg and said, oh, they were playing Super Smash Brothers. And Spencer said to Greg, I was at high school with this guy Alex, who wasn't called Alex really, but I went to high school with this guy who's really good at Super Smash Brothers. And then Nate, who met Alex at university, then went home and had been at high school with Greg and said, I met this guy at university who's really good at Super Smash Brothers. And then it turned out they were both talking about the same person. And I honestly could not understand what was going on until I drew this commutative diagram and discovered that they turned out that was the same person. So here's an example that's more obviously mathematical that I do with my art students involving relationships. So maybe we can remember what the factors of 30 are. It's not a joke that mathematicians are not necessarily good at arithmetic. We're not necessarily good at arithmetic, especially if we're thinking about something else at the same time. But the factors of 30 are 1 and 2 and 3 and 5 and 6. And 10, and 15, and 30. Yes, very good. So it's not very interesting. It's a bunch of numbers in a straight line, right? We live in a three-dimensional world, so we write on two-dimensional pieces of paper in one-dimensional straight lines. So we stuff our thoughts into one dimension when maybe they have natural geometry in higher dimensions and they don't want to go into one dimension. And I like to say this is why I do not tidy the papers on my desk, because they have natural geometry in higher dimensions. They don't want to be stuffed into one dimension. So we can uncover some of the natural geometry of this situation by looking at the relationships and by looking at which of these numbers are also factors of each other. And then we can draw a kind of family tree showing which ones are factors of each other. So 30 is at the top like a kind of great-grandparent. 6, 10, and 15 are factors of 30. 5 goes into 10 and 15. And just like the grandparents, we don't need a line directly from 30 to 5 because we can deduce it. 2 goes into 6 and 10, 3 goes into 6 and 15, and 1 goes into 2, 3, and 5. So now we see that it's the corners of a cube, which is a bit more interesting than a bunch of numbers floating around in a straight line, I think. And then there are many questions you can ask, like why? What other numbers make a cube? What other shapes can you make with numbers? And I do this with my art students, and one of them said, this is the first time I've ever been interested in finding the factors of a number. So there are many mathematicians in the room. Maybe you can see why this happens, right? It's because at the bottom level we have 2, 3, and 5, which are the prime factors of 30. The prime numbers are the ones that have no factors other than 1 of themselves, and 1 doesn't count for reasons that we'll see. But they give us the 3 dimensions that we can go along. And because they're different, they give us 3 different dimensions. And so if I then write out what happens, right, the next level up, everything has 2 prime factors. So if I write out the actual prime factors at each corner, we see that the bottom level, well, there are no prime factors at the bottom level. And then there's the individual prime factors, pairs of prime factors, and then the 3 prime factors. And then maybe you can look at it and go, oh, well, it didn't really matter that that was 2, 3, and 5. It could have been some A, B, and C. And people often say to me, I was fine with maths until the numbers turned into letters. I've now turned the numbers into letters, and I'm going to show there's a point. So we can try this again. We can immediately change the numbers and just try 2, 3, and 7. Well, 2 times 3 times 7 is 42. So here are the factors of 42. And now we can build the diagram from the bottom up because we have this new insight that it's about the prime factors at the bottom, the products of 2 prime factors, and then the products of 3 prime factors at the top. And then if we do the next diagrams, we can see that the middle diagram is the same except that all the 5s previously have turned into a 7. And then when we go up to the level of A, B, and C, it's actually the same diagram. So when you go up one more level of abstraction, it really is the same. And there's one more thing I want to stress in this picture, which is that 6 is less than 7, which does not sound very profound, but it's profound because 6 is higher than 7 in this picture. But 6 is less than 7. So we have 2 hierarchies going on the same set of numbers, and the hierarchies do not agree. And whenever in life you have 2 different hierarchies on the same set of people, if those hierarchies don't agree, it's a potential source of antagonism. For example, if there's somebody younger than somebody else in an institution, but the younger person is more senior, that's 2 disagreeing hierarchies. So the real point of going to A, B, and C at that level of abstraction is now we can take in many more examples because it didn't have to be prime numbers. It didn't even have to be numbers. This could be anything. And the mathematicians in the room know that this is subsets of a set of 3 elements. And those 3 things could be anything. For example, they could be 3 types of privilege: rich, white, and male. And then the next level down, we'll have people with 2 types of privilege: rich white, rich male, and white male. And then at the next level, people with only 1 type: rich, white, and male. And then at the bottom, people with none of those 3 types of privilege. So if I put in the remaining words, we get rich, white, non-men, and so on. And I'd just like to stress, whenever I talk about this, everybody in the room spontaneously identifies as non-rich. But we're all rich compared with some other people. I'd just like to remind us of that. So this diagram is important because it shows direct losses of privilege, and it helps us to understand something important that is a misunderstanding about the theory of privilege, because sometimes people think that the theory of privilege means that all white people are better off than all non-white people. And that's not what it means. Sometimes people point at some super rich black sports star and say, look at that super rich black sports star. See, that means there's no white privilege. But that's not what white privilege is supposed to mean. It's supposed to mean that if everything about you stayed the same, but you weren't white anymore, then we would expect you to be worse off in society. Now there's something else that's really important about this, which is that the people with 2 types of privilege, that's the second level down, there are no arrows between them because they're not comparable by a direct loss of privilege. But we can think about the absolute level of privilege that we think they have in society. And I think that rich white non-men, for example, rich white women, are probably better off than rich non-white men, who are in turn probably better off than, for example, poor white men. And the same is true at this level. And that actually it's even more skewed than that, because I think that rich non-white non-men are probably doing better than non-rich white men, especially if you think about some extremes like, say, Oprah Winfrey or Michelle Obama, who are definitely doing better than some poor white men in the middle of America who are unemployed and maybe homeless and who have really no hope for getting out of that situation. So I think it's like this. I think it's a cuboid. And it's like the fact that 6 is less than 7, but 6 is higher up. And I think this has helped me to understand why some white men are so angry about the theory of privilege, because they're told that they have 2 types of privilege, but they don't feel the manifestation of it because they're struggling. And I think that it's much more productive to understand the structural source of that anger rather than simply get angry with them in return. So moving on to sameness, category theory gives us more nuanced ways of talking about sameness. All equations are lies. For example, 8 plus 1. Does 8 plus 1 equal 1 plus 8? Well, if you're a small child and you're still adding up in your head, 8 plus 1 means you put 8 in your head and you count on by 1 and you get 9. Whereas 1 plus 8 means you put 1 in your head and you count on by 8, and that's really hard. So the point is that the processes are different, it's just that the outcomes are the same. And 2 times 5 is 2 packets of cookies, each of which has 5 cookies in it. And 5 times 2 is a waste of plastic. So the only equation that is not a lie is x equals x. And I believe I learnt this from John Byers many years ago. And then we christened this diagram the Byers equation, and then John got upset that such a trivial equation was named after him. So actually, it's not that all equations are lies. They're either lies or they're useless. Now, it's true that this is a bit clickbaity of me. They're not really lies. It's that there's something going on that's different on both sides. And the whole reason that equations are useful is that there's a sense in which something is different and a sense in which something is the same. And we use the sense in which it's the same to pivot between the 2 ways in which they're different in order to expand our understanding. And so having more nuanced ways of thinking of senses in which things can be the same helps us to make more pivots between situations. So category theory does this by invertibility. And invertibility is is undoing things. So if you add 4 to a number, you can always undo it by subtracting 4. But whereas, if you square a number, you're kind of in trouble, right? Because how do you undo that? You don't know which square root you're supposed to go to. So invertibility says that you can go there and come back. And both ways round that you go produce the identity. And this is what's called, this means that A and B are called isomorphic, and it's something to do with being able to reverse processes. So isomorphic objects are then treated as the same in a category, even though they're not actually the same. The category sees them as the same because the relationships with them are the same. And so this is the most technical slide in the talk. So if you're confused by it, then don't worry. So if you have these 2 isomorphic objects, and then you are another object X looking at A and B, your relationships with A are all the same as your relationships with B. Because if you have a relationship with A, this arrow, you can always compose it with the F isomorphism and get a relationship with B out. And then you could come back again by taking a relationship with B, composing it with a G, and then you get a relationship with A back. And so the isomorphic objects have the same relationships with X. It's kind of like if you're friends with identical twins, but you don't really do any different activities with them, then it's much harder to tell them apart than if you actually do separate activities with them. So things can be isomorphic in one category but not another. It really depends what you think and depends what you care about. So for example, one invertible, possibly invertible process is freezing and thawing. So if you freeze water and thaw it, then it will become water again, and that's fine. If you freeze milk and you thaw it, it depends. If it was homogenized, then it'll be all right. If it wasn't homogenized, it separates and it's a bit gross. So if you freeze an egg and thaw it again, something rather curious happens, which is this. And I'm just going to zoom in on it to show you. The yolk is just kind of sitting there. This is an actual egg I froze and then thawed and cracked. So usually egg yolks, when you crack an egg, they go more, right? This one did not go more. It just kind of sits there. And so that's really not the same unless you're not going to use the yolk. So I used to be quite large, and then I decided I didn't want to be anymore. So I spent quite a lot of time eating egg whites and throwing away yolks. And separating eggs is kind of a hassle. But if you've got a yolk like this, you just sort of pick it up and throw it out. So actually, it depends how you feel. Things can count as the same. So whole categories can also be isomorphic. And so, for example, the category involving the power dynamic, the structural power that male people have over female power. And remember, this is structural power. I'm not saying that every male person has power over every female person. I'm saying that men in society is structured so that men have more power than women. That is isomorphic to the power structure of white people over black people, which is isomorphic to the power structure of rich people over poor people. Whereas if you try turning the arrow around and making the male people analogous to the female people, that is not an isomorphism of categories anymore, because the arrow has switched direction. And this gives us a sense in which, when male people are sexist towards female people, there is a sense in which it is different from female people being sexist towards male people. And sometimes people say, oh, it's the same, women do it too. There is a sense in which it's the same, which is it's people being horrible to people. But there is a sense in which it is different, which is that the power structure is the other way up. So equality doesn't mean that men and women are actually the same. It's about when the world or the category that they're in should treat them as the same. And you may argue that there are some situations in which they shouldn't be treated as the same. There are some in which they're definitely not because of prejudice. There are some in which they really should be treated as different, like maybe the gynecologist's office. That's perhaps the only thing I can think of. So finally, context. Category theory puts things in context according to these relationships and says that we should consider things in context the whole time. So in these contexts, male people, white people, and rich people are analogous. And in these contexts, 30, 42, and rich white men are analogous. And we have a precise way of saying that, which is called an initial object. An initial object in a category is an object I such that for every other object there's a unique arrow coming out. So I is kind of at the beginning of things. So male people, white people, and rich people are the initial objects in those categories. And 30, 42, and rich white men are the initial objects in those categories. And when we move between categories, it enables us to compare the roles that the initial objects have in the different categories. So different people will be at the top or will be initial in different categories, right? So for example, in this category, rich white men are at the top. But if we restrict our attention to this part of the diagram, then rich white non-men are at the top. And we can entirely focus our context on women instead, and we could pick 3 types of privilege among women. For example, rich, white, and cisgendered. And remember, cisgendered means that the gender that you were assigned at birth matches your own gender identity. So now we see that there's an entirely analogous cube of privilege where rich, white, cis women occupy the analogous position that rich white men do in broader society. And this has helped me understand why there is so much anger towards white women in the certain parts of the feminist movement at the moment. Because if white women only consider themselves as underprivileged relative to white men, especially if they spend most of their time surrounded by white men, then they will forget how much privilege they have relative to other women. And then if you only ever see yourself as underprivileged relative to other people, and you don't ever see yourself as having more privilege than anyone else, that is another cause for antagonism. And we're all more privileged than someone and less privileged than someone else. And so actually I think that thinking about abstract structures can help us empathize with other people, because we can find a structure in which we occupy the analogous position that they do in another one. And so we can therefore understand what it's like to be in different positions in these structures. Which brings me to the slightly surprising conclusion, perhaps, that abstract mathematics can help us with empathy, because I think that abstraction is about analogies between situations, and that empathy is about analogies between people. So in conclusion, I would like to see mathematics taught more congressively, and I would also like to see more congressive mathematics taught. And I think that this, though without focusing on gender specifically, I think that it will be more inclusive towards people we could and may even want to value in mathematics, whose talent and possible contributions to society are currently being lost. And I think that category theory is an example of congressive mathematics that works at many levels and could help us include more different kinds of people in mathematics. And I would like to conclude by quoting one of my students from one of their final assignments, which is to write at the end of the semester how they feel about mathematics now. And this student wrote, "Now I find that maths is not just a tool, and the real reason for learning maths is to practice our thinking." Thank you very much.